All right, so in this fairly brief video, all I'm going to do here is just go over a few essentially practice questions where you can test to see to make sure that you've understood the whole mass spectrometry section, the two videos that you already watched. All right, so let me go ahead and here. Okay. These are just some sample questions to give you an idea of when you see these, how you're supposed to approach them. So here's a question. Assume you have two unlabeled samples, methyl cyclohexane and ethyl cyclopentane. How would you use mass spectrometry to tell the compounds apart from each other? All right, so sample A is which one? Methyl cyclohexane or ethyl cyclopentane. Likewise for B. So methyl cyclohexane would be this. Ethyl cyclopentane would be that. So how would you know whether sample A is the first one or second one? Likewise for B. That is what they're asking. If I hit each of these with a beam of electrons, I'm going to generate the parent ion here. What is the mass of the parent ion? Well, you can calculate. We have 7 carbons, that is 84. And you have 3, 4, 6, 8, 10, 12, 14 hydrogens. So 84 and 14 is, of course, 98. So you can identify this as the molecular ion peak, and you do the same thing for this one. And of course, the whole point is they both have the exact same molecular ion peak, so you can't really distinguish between them by looking at the molecular ion peak. So what you'd want to do then is you would, knowing what are the main fragmentation patterns, try to predict what would be the major ions here, maybe even the base peak, the most abundant ion, and that might usually lead you to the answer. So each of these is a ring. So one thing that we know is if we have rings, one way that these molecules like to fragment is to break the bond between whatever is the substituent attached to the ring and the ring itself. So break this. If that breaks, what I would expect then is to generate this as a fragment, and the plus charge would go on that carbon, meaning that the CH3 that you lose would be the radical, the CH3 being that CH3 there, right here. Now, I'll just put for completeness sake, it is possible, of course, that I would generate that radical and end up getting the methyl carbocation. That is possible. Less likely, because in the first case, that is a secondary carbocation. In the second case, that is a methyl, and the secondary is far more stable than a methyl. What would be the mass associated with this one, which is more likely, secondary one? Well, I've lost 15. So therefore, 98 minus 15 would be 85. In the case of the second one, same fragmentation we would expect there. So that would end up yielding this secondary carbocation and this primary radical most likely. Again, just for completeness sake for us as I'm working this, there is a possibility that that is the radical and that is the carbocation. But again, a secondary carbocation here is more stable than a primary here. So we'd expect it to be the first one. What would be the mass here? In this case, I've lost a 2 carbon unit, which is 29. So therefore, again, mass here is 98. If I subtract 29 from that, that would be 69. So let's look and see if that allows us to distinguish. When I look at sample A, right here, I see a peak at 69. That's actually the base peak. Whereas the base peak for B is this one, which is 81, 83. So did I do the, yeah, right here I made a mistake. I can tell this is 83. 98 minus 15 is 83. All right, and that's it. We've solved the problem because we predicted that the methyl cyclohexane up here, its most abundant ion is likely to be this one, which has a mass of 83. So just to clean this up for a second so that I can focus on it. We already decided the second pathway is not likely to be the case for both of them, right? So let us go ahead. So you notice for methyl cyclohexane, we would predict that the base most abundant fragment, i.e. the base peak, would be this one with a mass of 83, whereas for ethyl cyclopentane, we predict that it would be this one with a mass of 69. Right? So therefore, this one is sample A, and this one must be sample B. So you see how you approach these problems, right? You understanding how a molecule is likely to fragment will allow you to be able to tell which spectrum is for which one. Right? That's one type of problem that you are likely to see. So let me remind you here. Go ahead and just very quickly remind you. These are the things that you should remember in terms of major fragmentation pathways. So let's remind ourselves, if I have any kind of an alkane, right, let's say something like that, we have the molecular ion. Here we'll be breaking carbon to carbon bonds. So which is likely to be the most important fragment and the base peak? When I look at this molecule, I would predict that if I broke here, then that would end up yielding this carbocation, which is secondary, and this radical. I could also predict that if I cleave that way, then that would yield this carbocation, which is also secondary, and now the radical would just be that. And of course, if I cleave there, I could predict that I would end up getting this secondary carbocation, and the radical that I would get be that one, right? That's what we would predict. So what's the mass of my original molecular ion? I have 1, 2, 3, 4, 5, 6, 7. I have 7 carbons and 16 hydrogens. So 7 times 12 is 84, plus 16 is 100. So I know molecular ion would have a mass of 100. So this one, where I have lost a 2 carbon unit, which has a mass of 29, would therefore be 100 minus 29. So that would be 71. This one, the mass would be 100 minus the mass of the radical that I lost, which is 15. So that would be 85. And this one, the mass would be 100 minus the mass of a 3 carbon fragment, which is 43. So 100 minus 43 would be 57. So I would predict reasonably that my base peak is likely to be one of those three, right? That's what happens in the case of alkanes. Okay. What if instead of an alkane, what if we had an alkene? Well, again, remember, if you can cleave so that you end up getting an allylic carbocation, that is likely to be preferred. So if this were my parent ion, right, what would be the mass here? I see 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Let me put it this way. 1, 2, 3, 4, 5, 6, 7, 8. That would be 8 carbons. 8 times 12 is, of course, 96. And hydrogens would be 3, 5, 6, 9, 10, 11, 13, 16. So what would be 96 plus 16? 112. So here, I would predict that this would prefer to break so as to yield an allylic carbocation if possible. So one way would be if I cleave here, that would therefore yield the following, the plus charge here, that would make it secondary and allylic, and therefore the radical would be this 2-carbon radical. Now I could also break here, in which case I would predict that I would get this secondary carbocation and I would get a methyl radical. And I could also predict that I would break that carbon-to-carbon bond, which would therefore give me the following allylic carbocation here, and I would get a methyl radical. All right, notice in the first case here, secondary and allylic. In the second case here, secondary and allylic. In the third case here, primary and allylic. Secondary and allylic should be more stable than primary. So we would suspect that this secondary or that secondary would be more likely than the primary allylic. Of the two secondary and allylics, one thing that I do notice is that in the first case, I yield a primary radical. In the second case, I yield here a methyl radical, which is more stable, a primary over a methyl. So I would predict, if I had to, that this would be the base peak. What would be the mass here? Well, I've lost a 2-carbon unit, which is 29. So 112 minus 29 would therefore be 83. Correct. So I would expect that to be, I would predict that to be my main peak, which would be the base peak. But I would also likely get a lot of this. So this involves the loss of 15. So 112 minus 15, I would expect a significant, prominent, important peak at mass of 98. And here, this would also have a mass of 98, right? Now, obviously, you could also break carbon-to-carbon bonds, let's say here, but that wouldn't be allylic, and therefore you would predict that to be as important, right? What if I have an alcohol? Well, remember, alcohols can undergo two types of fragmentation, dehydration and alpha cleavage. So what would be alpha cleavage? Alpha cleavage is where the carbon that has the alcohol breaks its bond with a neighboring carbon. So I could break here. So if I say this is my molecular ion, I can find what the mass is. I see 6, 7, 8. I see 8 carbons, that's 96. And oxygen is 16, so that would be 112. And I see 3, 4, 5, 6, 8, 10, 12, 14, 16 hydrogens. So 96, 112 plus, what did I say, 16? So it'd be 128 would be the mass here. If I cleave as I've shown there, remember, the preference is to have the carbon here be the one with the plus charge because the oxygen can help resonance stabilize that like this. What would be the mass of this? So therefore, in this case, the radical that you would expect would be this one. Now, is it possible that this ends up being the carbocation? Well, it's secondary, It's reasonably stable. So therefore, it is possible. So I will still show that. That would be the radical in that case. Alternatively, the alpha cleavage would occur here, in which case you would predict that the preferred carbocation would be the one with the plus charge here, and that the radical would therefore be the methyl radical. The other one, to have a methyl carbocation, is less likely, so let's not even bother there. And this one has a mass, right? So what would be the mass? So let's just do it by counting. Here I have 2 carbons, that's 24, plus the oxygen, which is 16, would be 40. And I have 1 hydrogen here, which would be 41. I have 1 hydrogen here, 42, and 3 hydrogens here, 45. So something with a mass of 45. What would be the mass of this one? Well, I have 1, 2, 3, 4, 5, 6 carbons. That would be 72. And I have 1 plus 2, 3, plus 2, 5, plus 2, 7, plus 2, 9, plus 2, 11 hydrogens. So therefore, 72 plus 11 would be 83. And this one down here involves the loss of 15. 128 minus 15 is 130. So I would expect to see from the alpha cleavage, one of these is likely to be the base peak, 45, or 113, more likely, 83 possible. Then, of course, and I'll kind of block it off here, but I can scroll down. There's also the possibility of a dehydration. So if my alcohol is this one, we know that we're going to lose this OH plus a hydrogen from a neighboring carbon. So I can lose that hydrogen, or I can lose one of these hydrogens. So we already know this is our molecular ion. This has a mass of 128. If I lose this hydrogen, then what I'm going to generate is a molecule of water, which is neutral, and I will therefore end up with an alkene where the double bond is here. Therefore, that would be the molecular ion, the radical cation, the fragment. So the mass here would be 128 minus 18, which is 110. That'll be the same for all dehydration. There's also the possibility, of course, that I lose one of these hydrogens, in which case, along with the molecule of water, I'll just focus on this, I'll end up getting this as my carbocation, mass of 110. Can we decide which of those two is more likely? Yes, you can. Before I tell you, pause it here and think of how you'd be able to predict which of those two dehydration products is most likely based on what you already know from organic chemistry. Pause here. All right, so what you would invoke, of course, is Zaitsev's rule. What's the degree of substitution of that alkene? That is a tri-substituted alkene. What's the degree of substitution of this alkene? That is a mono-substituted. Zaitsev's rule says a tri is more stable. So we would predict that that would be the more important one. So therefore, I can reasonably predict 3 important fragments that I would get from the fragmentation of that alcohol. I can reasonably predict this one with a mass of 45, this one with a mass of 113, and this one with a mass of 110, and potentially a little bit significant amount of this one with a mass of 83. What if I have an amine? All right, so remember, in the case of amines, they undergo alpha cleavage. So if I have, let's say something like that, alpha cleavage means the carbon here that's bonded to the nitrogen will break its bond with the next carbon. So here or here, which is exactly the same thing, or this one, which has a nitrogen bonded to it, will break its bond here. So therefore, here's a molecular ion. What would be the mass of this one? I see 1, 2, 3, 4, 5, 6, 7 carbons, which gives me a total mass of 84. I see a nitrogen, which is 14, and I see 3, 6, 7, 8, 9, 10, 11, 12, 13, 16 hydrogens. So therefore, total of 84 plus 14 plus 16 is 114. 114. So if this is the alpha cleavage that occurs, then I would predict that the carbocation would prefer to be this one, the plus charge here. The radical that I would lose would be this one. The mass of this would therefore be 114 minus the mass of this 3-carbon unit, which is 43. So 114 minus 43 is therefore 71. So that would be an important fragment. If I cleaved here, let's say, then I would predict that the base peak is likely to be this one. The radical is therefore going to be this one. The mass of this would be 114 minus the mass of CH3, which is 15. So that would be 99. Which one is more likely? Well, this one here is secondary. This one is primary. So that's likely to be. Now you might say, but this is a methyl radical, whereas this is a primary, and a primary is more stable. But we only use that if we cannot make a distinction based on the nature of the carbocation and its stability. And here, clearly, a secondary one here is more stable than a primary, so there's no need to look at the radicals. Only if we had 2 secondaries or 2 tertiaries or 2 primary carbocations would we then move on to the radical to try to make a distinction. So I would predict that this one is likely to be the major fragment and therefore the base peak, right? So notice, right? You have to know what are the preferred fragmentation patterns that you have for molecule. I'll just do one more because you can always go back to the video where I discussed these. So let's say that I have, let's say an ester. So let's say that I have an ester like that. So we know that anything that has a carbonyl, so this would be a molecular ion, would undergo alpha cleavage here, alpha cleavage here. And we do know that in the case of esters, this oxygen to carbon bond likes to fragment. So I won't bother calculating masses here. You can do that. We'll just look at the fragments. You have to know how to calculate then what would be their masses. If I get this alpha cleavage, I could reasonably predict that what I would prefer to get would therefore be this, because again, the reason for this preference is that the oxygen here can resonance stabilize. I would find what that mass is, and I would predict that to be important. If I do this cleavage, I would reasonably predict that I would get this carbocation. I would find its mass, and I would predict that would be an important peak. And then finally, if this is the cleavage that occurs, remember, in that case, we would predict that the plus charge could be here. That's a secondary carbocation, stable. I would find out what the mass happens to be there. Now, in addition to that, remember, any carbonyl that has at least 3 carbons beyond the carbonyl could conceivably end up doing a McLafferty rearrangement. You tend to see these more with ketones and not so much with esters, but let's go ahead and look at potentially what happens here. So if my molecule, we draw it here, is this, I'll just rewrite it in a way where you can see the McLafferty rearrangement. So remember 1, 2, 3. Those are the ones of interest. So 1, 2, 3. and I'll just fill in here and say 4 and 5 so that we keep tabs. 4 here, 5 here. Number 3 has to have at least one hydrogen. The oxygen will take the pi electrons and grab the proton. These electrons will move in to form a double bond between 2 and 3, and the bond between carbons 1 and 2 will break, and these electrons move here. If you follow that movement from the left-hand side, what you're going to get is going to be this, which is 2, 3, 4, and 5. And from the right-hand side, what you're going to get, let me put it down here, is therefore going to be the oxygen now has the proton that it picked up. There's now a single bond here, and there is a double bond to this carbon that we labeled 1, and then you have that, and that, right? So this is going to be your radical ion. Whatever its mass is, you would predict to be an important, potentially an important fragment. And so on and so forth. You can go back and check those. So this is a reminder. These are the things you have to take into account when you're working these problems. That's how we knew here that breaking this bond here and breaking that bond here be the most likely way this would break. And you saw it allowed us to predict sample A is which molecule, sample B is which molecule. Here's another question. Two molecules A and B are shown below. Which one gives rise to the mass spectrum below? Okay, so let's do the same analysis. In other words, you want to predict what would be the major fragments you would get in each case, and that will allow you to tell which one it is. So for A, this is what I have. It is a ketone. It cannot undergo McLafferty rearrangement because you notice I don't have 3 carbons on either side of the carbonyl. But we know that these undergo alpha cleavage. So I could break here. So let's just go ahead. This is my molecular ion. The mass of this is going to be 1, 2, 3, 4, 5, 86. We see 86 here. If I do that, I would reasonably predict to have a methyl radical and the carbocation would therefore have the plus charge here. The mass would therefore be 86 minus 15, which would be 71. I could, of course, have this alpha cleavage, in which case I would predict that I would have the plus charge here most likely, and the radical would be this one. The mass of this would be 86 minus 43, which would be 43. Now, in this case, it is possible that the plus charge would end up being here because that's secondary, fairly stable. That would have a mass of 43 also, and that this would therefore be my radical. Now, when I look at the mass spectrum I'm provided with, there's 40, 41, 42, 43. So notice that the base peak here, it has a mass of 43, and we can quite clearly see 43, 43. It's looking like that, but we have to show what about the other one. So in the case of B, this is symmetrical. So if I break here or I break here, it's exactly the same thing. So this has a mass again, it's the same 86. So if I break here, which is the same as breaking here, I would get, in that case, I would predict that radical and that the preferred cation would therefore be this one. The mass would be 86 minus the loss of 29 here. 86 minus 29 would be 57. But that is not, right? You can see a 57 here, but that is small. It's not, since the base peak is 43, and I can clearly predict important fragments here of 43, but I don't really predict an important fragment of 43 for B, then I would say that this is definitely A. All right. Below are mass spectra for 4 different compounds. Identify whether each of these compounds contains a bromine, a chlorine, or neither. All right. So we pause here and you decide what you have here. And here are the other two. You can pause here and decide chlorine, bromine, or neither. Okay, so going here, how do I know if I have chlorine or bromine? I have to have an M+2 peak. So here I recognize the M+ peak there. I recognize the M+ peak there. This is my M+1 due to C13 is probably this one there. I don't see an M+2. So this is neither. There's there isn't bromine, there isn't chlorine in either of these two. I go here. Here now, however, I see the molecular ion here, and here I see an M+2 peak, right? So you notice whatever that is, then there's one here, then there's that one, M+2. They're about equal height. This is bromine. And here I see the molecular ion peak, and I see here the M+2, and this is about 1/3 the height of the M+1, so therefore this one has chlorine, right? So you see how you have to be able to recognize these elements. Now, you can be asked these questions in multiple choice format, same difference. Here's one. What's the mass of the most abundant cation formed by alpha cleavage of this? So alpha cleavage means the carbon that has the nitrogen bonded to it will break its bond with the next neighboring one. This one doesn't have a neighboring one to break with, neither does this. But this one does have a neighboring one, and that's going to be the alpha cleavage. Remember, in that case, we will prefer to have the plus charge on that carbon so that the nitrogen can help stabilize it by resonance by moving those electrons. So what is the mass here? Well, if this is a molecular ion, what is the mass? I have 1, 2, 3, 4, 5, 6 carbons. So I have 6 carbons. I have a nitrogen, and I have 3, 5, 7, 9, 12, 15. I have 15 hydrogens. 6 times 12 is 72, plus the 14 from the nitrogen would be 86, plus the 15 from the hydrogen would be 101. I am losing this 3-carbon fragment, which is 43. 101 minus what I lost, which of course is 43, is therefore going to be 11 minus 3 is 8, 9 minus 4 is 5. So the mass here is going to be 58. So this is probably the most abundant fragment this week. Oh, good, Tom. All right, one more here and then we'll be done. This one is a little more complex, so I use this example. The mass spec of nitromethane shows major peaks at 61, 46, 30, which is a base peak, and 15. Which statement is inconsistent with this data? All right, if what I have is my molecular ion, this, what is the mass? 15 for the CH3 plus 14 from the nitrogen is 29, plus 32 from the 2 oxygens is 61. So then that must be molecular ion peak there. So if I break, and I'll just, maybe I should have drawn it this way, the bond there. So it makes sense that if I break that bond, I could end up having the plus charge here, and therefore this would end up being the radical, and the mass here would end up being 15. And it is possible that this is the radical, and therefore the ion is going to be this one, which would be 61 minus 15, which would have a mass of 46. So this one would account for that. This one would account for this. The third is the one that we really haven't accounted for. Let's look at our choices. So which statement is inconsistent with these data? All right, A says carbon to nitrogen bond cleavage occurs. That is consistent. That's what we're saying here, that we're cleaving this carbon to nitrogen bond, because that is consistent because it helps explain the 15 and the 46. So that's not it because we're looking for the inconsistent. B says NO2 plus is not formed as a fragment. Here we see a fragment that's NO2 plus that has a mass of 46, and we do see that there. So therefore, this is not a consistent statement because it's contradicting what we're seeing. And we can finish off. C says the parent ion is observed. Yes, because the parent ion would have a mass of 61, which is that. So that is observed. So that is not inconsistent. And this says NO plus is a fragment ion. Well, we don't see a fragment ion. However, what would be the mass of NO plus? 16 from the oxygen, 14 from the nitrogen. This would have a mass of 30. That is what would account for this. We're not really required to explain how it happens, what happened. We're just being asked to check statements, and that would not be inconsistent because it would explain the 30. The only inconsistent one is B, as B says NO2 is not formed as a fragment. Yes, it is formed as a fragment, so that is an inconsistency. And that would be a couple of examples of multiple choice type questions that you could have here. Right, so this is just to give you an idea of types of questions and how you should approach them.